Okay, so we're in the last chapter. We've been talking about sort of kinetics in this chapter. Um, kinetics, obviously, as we talked about previously, deals with really sort of the rate of a reaction. So, kind of really how fast or how slow a chemical reaction will take place. We've talked so far in this sort of chapter about a couple of different things. The first thing that we sort of looked at is was referred to as the rate expression, and the rate expression is the sort of the change in concentration over time um, for a particular reaction. And we saw that you basically can use the balance coefficients in the equation to help you with the stoichiometry part of that. And again, it allows you really that if you know just one piece of information about a particular reaction, maybe you know how the reactants are changing over time, maybe you know how the products are changing over time, you really can use the rate expression to figure out how everybody else is changing over that similar same period of time. You could also use it to basically figure out the average rate of a particular reaction as well. Remember that when we do that from the balance equation, we do 1 over the coefficient. Again, that 1 over the coefficient really takes care of the multiple relationship when you're doing those type of calculations. Um, we also put a negative sign for our reactants as we would expect them to be decreasing with time, while our products do get a positive sign as they should be increasing with time. So we saw a couple examples where we can do that to really, again, get sort of these rates at how everybody is changing over a period of time and a particular reaction. We also talked about writing the rate law, and the rate law has sort of a general form like we see up here on the top right. So this is really a rate law. By the way, this is again a rate expression here on the left there. But the rate law is one that basically deals with just the reactants. So when we write rate laws, calculate rate laws, it's really all about the reactants. It has nothing to do with products. So products are never included in it, just your reactants. And we get these sort of rate is equal to the rate constant, which is the lowercase k, times the concentration of your reactants to some order. And that order is found experimentally. So those are the type of problems, as we did a number of them the other day, that you typically will be given sort of table information. So you'll be given the concentrations of your reactants. You'll be given the initial rates that happens in these different sort of experiments. And you can mathematically sort of determine the orders for each reactant. And again, that's where we use sort of that formula like rate 2 over rate 1 is equal to k, kind of a to the x, b to the y, and on the bottom, obviously, k, a to the x, and b to the y. So this is when we use that sort of table information, which is a very common kinetics type problem that's given to you. You use that table information. You want to find at least two entries where one of the reactants remain constant and the other one varies. Or again, if you maybe have three reactants where two of them remain constant, one of them varies. The point of that is again, so you only have really one unknown. We could do some math like we did in some of those examples and basically figure out the order for say A and the order for say B. And those again can be found from those tables. Once you have those individual orders for the reactants, you can basically add them together, and that will give you what is referred to as the overall order for a particular reaction. Um, and once you have all that sort of done, you then can go back to the table and really find the value of K, where again, if we have multiple entries into that table, you could choose any entry you like, and you basically put it into the rate law with the orders and actually get the value of K. Um, and then we sort of got into sort of more specific orders of reactions. And the one where we kind of finished up on last time, I think, was first order reactions. So first order reactions, as we talked about last time, obviously, a lot of times we'll have one reactant to the order of one. Um, and important in kinetics is the rate constant and the units associated with the rate constant. So as we spoke about last time, when you have a rate constant that has units 1 over seconds, reciprocal seconds, that is always going to be a first order reaction. And again, in kinetics problems, they don't oftentimes in sort of blinking lights say, hey, this is a first order reaction or a second order reaction or anything like that. They will just sort of give you the value of the rate constant with the units. And from seeing those units, you should be able to recognize that it is a first order reaction. So the common units for a first order is 1/2 seconds. Again, as I mentioned last time, it does not necessarily be seconds, is really 1 over some unit of time is typically what we see in terms of those units. Again, seconds, common unit, because as we talked about, we don't usually run a reaction for days on time or weeks on time. So seconds is usually a very convenient sort of unit, but it doesn't necessarily have to be seconds. With our first order, as we talked about, there are really two graphs associated with it, but really the one we sort of highlighted here at the end, and it's on the right, is really the main graph that we see in a first order, and that is happens when you take the natural log of a on the y and time on the x. You will get a linear relationship, and the slope of that line will equal the rate constant. And that comes from what is known as sometimes the integrated rate law here, or so sort of the concentration time dependence sort of equation. And for a first order reaction, it is the natural log of a is equal to the natural log of a naught minus kt. A is the concentration. A is sort of the final concentration. A naught is the initial concentration. K is our rate constant. And again, T here is time, not temperature. You do have to, as we talked about with this one, usually watch units here in terms of the time. So between K and T, sometimes they are different units. They really can be any unit you want as long as they are the same, so they do cancel. And associated with that, I think I jumped the gun as well last time, but we'll see it here in the slide or not. But there's also a half-life equation that goes with the first order, and that is it right there. The half-life for a first order is the natural log of 2, which if you punch that in on your calculator is like 0.693 divided by k, which is the rate constant. And sometimes, or in a lot of kinetics problems, you will sometimes have to use both of those sort of equations together. Very, very common is you're given all the information except for the rate constant, but you're given the half-life for a particular reaction. So it's a very common sort of calculation where you use the half-life equation to figure out the rate constant. And then once you have the rate constant, you could actually stick it into your sort of integrated rate law here and solve for what you're looking for. So important things on this slide is some stuff that I highlighted and we talked about last time. Again, the units associated with that first order, the half-life equation, the integrated rate law, and the graph that typically goes with that. So if you're asking, are you asking about this equation here? This equation and really this equation is the same equation. It's just that they basically took the natural log of this equation all the way across. And that's how we get to the guy on the right. And I would say probably 99 times out of 100, the guy on the right is the equation that most people use or sort of display as sort of the first order reaction equation. But they are technically kind of the same reaction. Just one is the natural log all the way across on that. Just like technically this graph that we see here on the left is also technically a proper graph for a first order reaction, which is the concentration versus time. So the difference between the two graphs, the one on the left is concentration on y, the one on the right is the natural log of concentration versus time. But as we will see very shortly, this is also a graph that we see for zero order, but it's more linear in a zero order sort of graph. So sometimes they both sort of pop up. But I would again say 9 times out of 10, graph on the right is really the one most people think about in terms of a first order reaction. Other questions on that? So here's just a first order sort of plot here. Again, you can see you get a very linear relationship. And if you take the slope of it, it does equal minus k here. Again, the minus is important because this is a negative line, which means when you get the slope value, that's going to be negative. This will be negative, which will turn your k into a positive number. And typically your rate constant is a positive number. So again, that's why it's sort of important. And again, this equation comes from rearranging that first order equation like so. And this is basically that equation in the form of a straight line, y equals mx plus b. Again, y, the natural log of a, x being the time, and again, the slope being negative k in this particular case. Any questions on that? All right, so why don't you give it a try here? This is first order. How long will it take to decrease from 0.88 to 0.1? We got there 1.4. Why don't we do? We'll do seconds. How many seconds will it take? Why not? Seconds, which automatically tells us it is first order. So again, sometimes they may leave that little part out and just sort of give you this number, and you need to know that that is first order so that you could use this. We have our initial and our final concentration, initial being 0.88, final being 0.14. It's a reactant, so it's decreasing with time. And we want to know how long it will take. So we're looking for t in this case. So basically we have the natural log of 0.14 is equal to the natural log of our initial 0.88 minus our rate constant, which was 2.8 times 10 to the minus 2, and we go on a diagonal, and our t going that way. So really a couple ways you can solve it, but probably the easiest way is just to take the natural log of 0.14. You then would subtract basically the natural log of 0.88 to the other side. So subtract the natural log of 0.88. And if you happen to get a number somewhere in that ballpark, you got like a negative 1.838279 is equal to minus 2.8 times 10 to the minus 2 reciprocal seconds times t. Dividing that to the other side there, going to get us, we'll call it about 66 seconds. Sounds good. Our time would be 66 seconds. Again, seconds coming from our reciprocal seconds. When we divide, it comes to the top and becomes seconds in this case. Any questions on that particular one there?
What's the number there on the left, right above 66 seconds?
It's a really badly written 1.838279. It's a bad two right there.
Thank you.
Other questions? And that's what you get when you take basically the natural log of 0.14 and then subtract the natural log of 0.88. All right, so let's continue on then here. So the half-life, as I sort of jumped in a little bit earlier on it, for our first order is the natural log of 2 over k. And again, sometimes you will see it as 0.693, which is basically what you get when you take the natural log of 2 on your calculator. So if we want to know what the half-life of this, that decomposes at a rate constant of 5.7 times 10 to the minus 4 reciprocal seconds. Again, we know we would want to use the first order half-life because of the units that we see here. So basically our half-life would just be plugging it in. We have 5.7 times 10 to the minus 4 reciprocal seconds. So again, we end up with, it looks like, about 1,200 seconds, give or take here. You go something a little bit bigger than that, but the only number that we have here is 2 sig fig. So that's why we went to 2 significant figures on this. And as I alluded to earlier there, the reason we know it's first order, is the units that are associated with K, which in this particular case are reciprocal seconds. If you can't really remember per se, a half-life equation, we're going to see a couple of different ones as well. The half-life really just comes from, when you take this equation here, and if you're, not too bad at math, basically what that means is this guy would be the natural log, like you see here, of the initial divided by 2. That's basically the half-life, right? And again, here you could solve for T, which is what they did here. And that's basically how you get to the half-life sort of equation. Or you could just remember it, which would probably be an easier move, I imagine, in that case. Any questions on that? And this is again basically what the half life means. Sort of what we talked about is really the time it takes for half of whatever you started with basically to go away. And as we can see here in a first order sort of equation, we do see sort of this gradual decrease with time. So obviously here would be our first half life or second half life. By about the time you get to say 10 half lives, pretty much everything's kind of gone at that point. Um, but you know, in a first order reaction, it's only dependent on the rate constant or the rate of the reaction. It's not really dependent on any sort of initial concentrations or anything like that. It doesn't have any effect on sort of the half life. Um, as you'll see, if you take 200B radioactive decay, all radioactive decay basically follows first order kinetics. So these are the same sort of formulas that you would use in any type of nuclear decay or radioactive decay sort of process is first order as well. All right, so why don't you try another one here? We want to find the concentration of this after about 865 seconds. If we have an initial concentration of 0.0225, so see what you come up with. Take a look and see here. So in this particular case, we're looking for really the final concentration here. Again, they were nice enough to tell us as first order. If they didn't tell us it was first order, again, we can determine that by seeing the units here associated with the rate constant to tell us that it's first order. We do have the initial concentration. We do have time. So if we look at our equation here, we pretty much have everything on the right-hand side here. We are missing this guy. That's what we're looking for. So we could really just plug it in. So natural log of A going to be our initial, which in this case was 0.0225, minus our rate constant, which was given to us 2.9 times 10 to the minus 4 reciprocal seconds, times the time in this case, which was 865 seconds. And this is again the area where if you use this equation, you want to make sure you watch out on the units here. In this particular case, they are both in seconds, so we're all good on that, but very common. They are not always in the same unit, so you do want to watch that. So if we kind of clean up everything on the right-hand side, it looks like we will end up with natural log of 0.0225 minus 2.9 to the minus 4 times 865. Looks like we get like a minus 4.0450. I don't feel like rounding today. 8997 in this particular case. To get rid of our natural log on the left-hand side, we basically need to take E of both sides. So you need to take the E of that guy, and you need to take the E of this guy here. And when you do that on the left-hand side, it just becomes A. And if we take the E of the other side there, and that is definitely not the right button. Try that button there. There we go. Looks like we end up with 0.01, and again here 7.5. Units here will be molarity since we're looking for a concentration, so we do need the units. First off, any question on that calculation?
Yeah, I had a question about the graph. So is this just a straight line, or is this the curve?
Are you talking you talking about just in general? In general, if this is a first order reaction, if you were to graph, say, an experiment of this, um, if you decided to do, say, A versus time, A in this case would obviously be this guy. Yeah. And if you just did that graph, what you would see is, and again, a very badly drawn one here, not a linear relationship, but you'll see the sort of that decrease with time. And most often, though, if you did the first order graph, you would do the natural log of A here, which again, A would be this guy versus time. And that should yield you a fairly linear relationship in this experiment. If you did, say, multiple experiments or something like this, or even um, multiple sort of experiments, or even this particular one here, and you would get that where the slope of this would be minus K. So Again, first order, most often people look at this graph. And again, if you sort of graphed experimental information and did this graph, this would probably be your most linear sort of bet of what it would look like, stuff like that. And as we'll see, we're going to talk in just a second here about a couple of different orders of reactions, like second order and zero order, and they have different graphs. So that's one way you can potentially determine the order of a reaction is sort of through graphical linear graphs, and whichever one's the most linear will sort of tell you, hey, that's a first order reaction, or the second order graph with more linear, that would be a second order stuff. Yeah. Other questions on that? Okay. We could also just make sure that it does sort of make sense, and it does, right, because it's first order and all that, and it's over time. We should expect this to be decreasing with time, which means again our final sort of concentration here should be less than what we started with. If you ended up getting more than what you started with, definitely something's going in the wrong direction. Probably screwed up the calculations somewhere along the way. Other questions on that? Questions on first order reactions. And again, really kind of, a couple of ways you could achieve sort of a first order reaction. A lot of times it's something like a decomposition reaction where you have one reactant to the first order. You could potentially have, say, two reactants where one is first order, one is zero order, to get an overall sort of first order reaction. But most commonly, probably like a decomposition type reaction is probably taking place. All right. Then we're going to skip this kind of the half-life. So we're going to talk then about second order reactions. So second order reactions, it's another sort of, I don't want to say popular, another type of kinetic sort of reaction that we come across a lot. And this could also be achieved sort of a couple different ways. You could technically have sort of one reactant that is to the second order. You could have perhaps two different reactants where they're both first order, and that would get you a second order reaction overall. So again, multiple sort of ways that you could kind of achieve a second order reaction. This is our rate expression and sort of our rate law here, where the rate is equal to K times A to the 2 or squared. Again, if we sort of solve for K, just like in first order, if we see the units associated with a second order reaction is actually different and is actually 1 over molar seconds, or sometimes written m to the minus 1, s to the minus 1. Again, here, just like first order, the seconds part doesn't necessarily have to, or the time part doesn't necessarily always has to be seconds. It could be minutes, hours, days, but it's usually 1 over molar, some unit of time. Again, tells you that it is a second order reaction. And because it would be a second order reaction, it actually has a different rate law that deals with concentration versus time. And that is 1 over A equals 1 over A naught plus KT. And if we rearrange that and write it a little bit differently, we get 1 over A equals KT plus 1 over A naught. And that is written in the form of a straight line. Y is equal to mx plus b. On the y would go 1 over A, which is what we see here. On the x would go time. And when you do this type of graph, you will get a linear line. This line is actually with a positive slope here, which, as you can see here, means the slope is equal directly to the rate constant in this particular case. So to sort of touch upon what I was just speaking about in terms of the graph, if you sort of took your experimental information and you did, say, a natural log of A versus time, and you did a 1 over concentration versus time graph, and what you see is, say, the 1 over A versus time graph is more linear than the other graph, then that reaction would be second order. How do you figure out if it's more linear? Well, you could do like an Excel graph and do like the R squared value there, right? R squared value closest to 1 is most linear. And that's a way you could sometimes do that when you do like a linear regression sort of graph, best fit line, like an Excel or something like that. We also see that this graph is actually a positive line, different than our first order, which is a negative slope. And it also has a different half-life equation. The half-life in a second order reaction is 1 over K and the times the initial concentration. So unlike a first order reaction, the the half-life is dependent on the initial concentration that is present. So much like sort of all of our other ones here in terms of importance for realizing what's sort of second order and stuff like that, the units again associated with K is really important. This again is the one that we want to use specifically for a second order reaction to figure out concentration versus time. Then obviously our half-life is different, and our graph that is typically seen for a second order reaction. So those are really the important parts off of this sort of slide, especially when you're dealing with, something that's maybe second order. And again, really, like I said, very, very common. They do not, lay up sort of like, here's what order it is. They just give you that rate constant. So really knowing those units associated with that case is really important to solving these problems a lot of the time. That also brings us to the sort of the last type of reaction that we'll talk about, sort of the most common sort of reactions, and that is what is referred to as a zero order reaction. And in a zero order reaction, usually you'll have one reactant that is to the zero order. So if you take something to the zero, it is equal to 1, basically, right? And that means that the rate equals K. So what we see for the rate constant for a zero order reaction is it has the same units associated with the rate, and that's molarity over seconds. So those are 3 distinct different units that you see, and they tell you sort of what reaction you're dealing with or what type of reaction you're dealing with. Again, if you see 1 over seconds, that is your first order reaction. If you see 1 over molar seconds, that's your second order. And if you see molarity over seconds, that is your zero order. It has a rate law very similar to first order without the natural logging of it there. So it is the concentration equals the concentration initial minus KT. Just like all the other ones, if you sort of rearrange this and rewrite it in this fashion without the natural log there, this is our y is equal to mx plus b. Again, on the y, we have concentration. On the x, we have t, which is time. And that should yield you a straight line, where, as you can see, the slope is equal to minus k. This, again, is the same graph that we saw for first order, except if it is a linear relationship you get when you do this graph, it is zero order. And again, just to remind you that for first order, what we saw was not a linear relationship for this graph. So you get this one for first order. So again, sometimes you may see both of those, but this is definitely the one associated with zero order. It should give you a linear relationship when you graph it. Also, you can see different half-life equation as well. Half-life is the initial concentration divided by 2K, which means also the half-life for a zero order is dependent on the initial concentration as well. So same sort of important things here for sort of remembering. It's zero order, those units. Want to make sure you use that equation and this equation if necessary. And again, our graph here, which is typically what we see for our zero order. So those are the 3 sort of common orders: first order, second order, zero order. And again, if you think about a lot of reactions that you see or deal with, most of the time in terms of how many reactants you have, you have things like 1 reactant, 2 reactants, occasionally 3 reactants, but you don't really get much more than that. And these are the sort of common orders that sort of result for those sort of combinations of different amounts of reactants that come together. Again, in this case, you would need probably like maybe 1 reactant again, that is to the zero order and sort of its relationship. Any questions on that? All right, so why don't we try one here? This is second order. We have an initial concentration after 5 seconds. It is 0.001. What is the rate constant here? So take, again, in this case, they probably would need to tell you that because there would be no way for you to figure it out. So we do know that 1 over A is equal to 1 over A naught. And again, this is the only one that's plus KT, as we get that positive sort of slope. We have our, what we got there? We got our initial. We have our final and we have our time in this case. So our final was 1 over 0.001 equals 1 over our initial, which was 0.01. And that's going to be plus our k, which is 5.0 times 10 to the 2 seconds. And we're solving for t. Same sort of move here, probably. Take 1 divided by 0.001 and then subtract this guy to the other side and then divide it. So if we do something like 1 divided by 0.001 minus 1 divided by 0.01, going to give us 900 is equal to 5.0 times 10 to the 2 seconds. Again, we're going to divide that to the other side, and that would get us, looks like 1.8 units here would be, that would not be that. We are actually solving for K. So there we go. Try K there. So used to time. So this is molarity. And we're dividing this and solving for K. So this would give us K, numbers right, 1.8. Units would be 1 over molar seconds in this particular case. And again, that is what we would expect it to be for our second order. And again, when we do this sort of subtraction, we end up with 1 over molarity. When we divide, seconds ends up on the bottom, and we end up with 1 over molar seconds. Any questions on that particular one there? Okay. So here's just a sort of a summary table of what we talked about in terms of the different orders, 0, first, and second, and sort of our concentration and time equations and our half-life equations. Again, if you're sort of good at math and you can't remember the half-life, you could always substitute in, initial divided by 2 into here and solve for t, and that would get you here. If you ever run into a jam, you need to kind of figure it out and you can't remember it. As was mentioned before, since these each really do have a sort of specific graph associated with them, this is a very common way, sort of experimentally, that you can determine the order of a reaction. You basically just do a whole bunch of concentrations versus time data in an experiment. And basically you do all three graphs. You do the first order graph, the second order graph, and the 0 order graph. And, whichever one is the most linear, whichever one basically gets you the straightest line, whichever way it may be going. And again, usually you could determine that by the R-squared value closest to 1. That's the linear coefficient when you do sort of a best fit line. That will graphically sort of determine, which one is what the order of the reaction is. And again, that's why it's important to know those graphs that are typically associated with these orders of reactions. Any questions on that? Okay. So the next thing we're going to talk about is sort of temperature and energy sort of relationship with the rate. And let's take a look at that. So these are basically energy diagrams. I think we might have touched upon them a little bit before, but these are essentially energy type diagrams. And there's two types. One on the left is exothermic, which means heat and energy is released. In terms of exothermic, usually we look at enthalpy, and that's a negative value. Guy on the right is endothermic, which means heat and energy is typically absorbed. And one way to represent that usually is delta H, which is our enthalpy, and that usually is a positive sort of number associated with it. How can you recognize sort of the differences between these two? It is really the placement of where the reactants are in relationship to their products. So when we look at our exothermic reaction, our reactants are here, and they are higher in energy than our products, which means sort of energy needs to be given off for our reactants to get down to our products. And that's different than when we look at an endothermic reaction. Our reactants are lower in energy than our products. So in order to sort of get up there in terms of our products, we need to put energy in to do that. And that's really the basic way that you're able to sort of figure out the difference between these two graphs. What happens as we sort of go from reactants to products is basically everybody here's got to break their bonds, and everybody on this side needs to make the bonds. And that's sort of the process that's happening as we sort of climb this hill. We have our reactants, they're starting to break bonds. They're also starting to make some bonds along the way here. And we get up all the way to the top of the hill here. This is sort of the highest point in terms of energy. And this is what is sometimes referred to as the transition state. And that's sort of the highest point in terms of energy. And what we have up there in that transition state is what is sometimes referred to as the transition state complex. Our activated complex. So transition state or activated complex is this guy right here with the weird symbol. This guy basically. And basically what this guy is something that has sort of partially broken bonds. It has some partially made bonds. So this is really sort of unstable in that sense because it's starting to break away all of its bonds, but haven't completely broken apart all its bonds. And it's starting to make new bonds, but hasn't completely made all of the new bonds. And one thing that we know, hopefully, about energy is the higher something is in terms of energy, the more unstable it is. It doesn't really want to be very high in energy. Things typically like to be low in energy. And what usually happens is pretty quickly our transition state complex sort of drops down to the other side to make products. It usually is something that's very hard to isolate because it doesn't hang around a very long time because it has these partially made bonds, partially broken bonds. But in sort of both graphs, what we do see is there's this hill that basically the reactants have to climb to get to the other side. And this hill is what is known as the activation energy, E of A. This is the activation energy. And really, the activation energy, as it says on the bottom there, is the minimum amount of energy for a chemical reaction basically to take place. It is, as you can see in these sort of graphs here, the hill that the reactants have to climb in terms of energy to get to the other side. And that is why when we talk about sort of reactions happening, really two things has to occur for a reaction to take place. There does need to be a collision. They need to actually collide in sort of the right spot in each of those molecules. And they need to collide with the right amount of energy basically to kick off that reaction, which is basically to get up and over that hill to the other side. What we see here is the activation energy is from the reactants to sort of the top of the hill, as you can see here. And over here from our reactants in terms of energy to the top of the hill. And what we see is our endothermic has a much bigger hill to climb. And that does make sense. This is endothermic. You got to put some heat and energy in there. And as opposed to, say, an exothermic where you got plenty of energy, they kind of get up and over to the other side. So these are, again, where sometimes referred to as energy diagrams. Guy on the left, exothermic, higher energy of reactants versus products. Guy on the right, endothermic, lower energy of reactants versus products. And again, that hill to climb to the other side is that activation energy. Clearly, the size of that hill has a tremendous effect on how fast or slow a reaction would take place. The bigger the hill, probably the slower the reaction would take place. And that's why sometimes increasing the temperature can help a reaction speed up, because when you increase the temperature, you get a greater proportion of molecules that basically can get up and over to the other side of that hill, as opposed to, say, at like room temperature or natural sort of normal temperature. Any questions on that there? This is what is sometimes referred to as the Arrhenius equation, and we'll see probably a more useful version of this. This is sort of the non-natural log version of this equation. But these are all our normal guys here. This is our rate constant. E of A is our activation energy. R is the gas constant, and actually is the 8.314 version of it, the one that has to do with energy. So it's this guy here. T is our temperature, like most things in Kelvin. A is what's known as the frequency factor, and essentially it is the sort of proportion of molecules that have enough energy to kind of get up and over that hill to the other side. So that's essentially sort of what the frequency factor is. We'll see probably a more useful relationship here of this equation in just a second, where we sort of take the natural log of that equation and we get sort of a graphical version of it as well. So again, that activation energy, that hill that needs to be climbed to get to the other side. And as I mentioned before, that sort of barrier is what is referred to as the activation energy. And when you get to the very top of that hill, which is the highest in terms of energy, that is where you get really that sort of, I'll call it an intermediate. It's sort of referred to maybe sometimes is that guy that's sort of partially breaking apart while it's trying to form some new bonds. And again, sort of a very unstable sort of situation in that because that's very highest in energy, and again very much will kind of drop down to the other side relatively quickly because of that sort of instability. Sort of a graphical relationship of what we see here in terms of the rate constant and temperature from the Arrhenius equation, which is sort of what we're looking at here, is what we see on this next graph here. And again, what we see is the relationship between temperature and the rate constant. As the temperature increases, so does the rate constant, which essentially means that the rate of the reaction also increases. As obviously, if we look at it the opposite direction, we kind of lower the temperature, we see a significant drop in the rate constant. Now, this is basically the natural log version of this equation here. And most of the time, sort of the version of the Arrhenius equation that we sometimes will see most of the time. And this is actually written in the form of a straight line. So this is y is equal to mx plus b, which as we'll see in just a second is the typical plot that we do for these type of guys where we're looking at sort of the temperature relationship versus the rate constant. And that means that if we sort of turn this into a linear relationship, on the y would go the natural log of k, on the x would go 1 over t in Kelvin, and that will give you a linear relationship. And sort of the importance of this is you can sort of graphically use it to determine something like the activation energy, which would be this part of it. And from here, as we will see, the slope is equal to minus E of A over R. Same idea. We could use the slope here to figure out the activation energy because this is a constant value. So in terms of the Arrhenius equation, sort of graphical ways of doing it, this is a very, I'll say popular, very common version of the equation that's used. And again, that's basically your linear relationship between temperature and the rate constant. But what we really see here is what we see on this graph. Basically, as you increase that temperature, essentially what you're doing is giving everybody more energy. Guys with more energy have enough energy to kind of get up and over that hill to the other side, thus increasing the rate of the reaction is typically what happens. And obviously vice versa, if you sort of go the opposite way, you lower that temperature, things now have less energy. You're going to have a less proportion of molecules with enough energy to climb to the other side, and you would see a decrease in terms of the rate of the reaction. Here is sort of that linear plot that is very commonly sort of used in looking at temperature and the rate constant. Again, it is temperature here. People are always into time at this point when we start doing kinetics, but again, that is temperature. What I was going to say before is if we do take the slope of this, it does equal minus E of A over R. And because this graph is always usually a negative graph, we will see that the slope would be negative equals negative E of A over R. The two negatives there is going to turn your activation energy into a positive number, which is what it should be as well. So when you calculate the activation energy, it's usually a positive number. And you can see that from those graphs we saw earlier. That is the hill, basically, right? So this hill It's sort of putting energy in. It's a hill they got to climb. So usually this activation energy is a positive number when you calculate it. Any questions on that? Maybe not super important here, but maybe it is. Just to look at this part of it here. And in terms of units, so very common activation energy is given to you in kilojoules, and R is obviously in joules. So sometimes you do have some unit situations that occur there between those two. So you do want to make sure you watch the units. When you do a calculation involving this, you got to either pick kilojoules or joules, and make sure they're in the same unit. Otherwise, you again will be off, obviously, by a factor of 1,000 there. This is sort of what we've just been talking about, sort of that energy barrier and basically the frequency factor is, again, that proportion of molecules that really does have enough energy to get up and over to the other side. The units of A usually will end up actually being the same units as the rate constant. So if you're ever interested in sort of what the units of A will sort of end up being, is usually pretty much identical to the units associated with the rate constant in that particular reaction. And again, as we talked about here, and as we saw, basically increasing that energy gives everybody more energy to get up and over to the other side, and thus obviously increasing the rate of the reaction. And that's what this graph sort of shows. Our graph in red is a higher temperature than our graph in blue here. I'm sorry, opposite of that there. And what we see is, our graph in red is higher temperature than graph in blue. And what we see is this is basically our activation energy. So when we look at sort of our lower temperature, only this proportion of molecules have enough energy to basically get up and over to the other side. When we increase that temperature, we now get this amount of molecules, obviously a lot more molecules that have sufficient energy basically to get up and over to the other side. And obviously, if that is the case, we would expect the rate of that reaction to increase as a result of that. And again, you could obviously look at this in the opposite part, going from one to the other, and you would have a lower amount of energy. Any questions on that? Here's like the fourth version of that equation in case you missed it the first 3 times. That's the same one that we've seen. Any questions on that guy? I will say as well, this is typically an equation that, a lot of times you usually won't sort of use sort of to solve a problem mathematically. This is usually sort of the one that's strictly a lot of times used for graphical sort of solving of this. And then sort of a problem, what you would be given is you'd be given a bunch of K values and you'd be given a bunch of temperature values. And to do this graph, you would have to take all those K values and basically turn them into the natural log. You would have to take all the temperature, make sure they're in Kelvin, take 1 over the temperature. And those would be your points that you would graph on a graph like this. And usually you would, again, use this more sort of graphically and finding the slope. And you could also use the y-intercept, which is what this is, B, to figure out the frequency factor as well. So why don't we look at sort of an example of sort of how a problem like this would be sort of given to you. Again, you would be given sort of a table such as this, a bunch of K values, a bunch of temperatures. They were nice enough to give it to us in Kelvin. Sometimes they will give it to you in Celsius, so you need to convert it to Kelvin. And then basically what you need to do is take all those temperatures and take 1 over the temperature in Kelvin. Let's go 1 over T better. You got the K value here. You need to take the natural log of K of all those. And again, those would give you points that you would do, sort of like an XY scatter plot if you're using like Excel or something like that. Add a trend line, best fit line, get the equation and the R squared value. And if you did all that, it would end up looking something like what we see here. And again, you would get that equation from that straight line. Probably wouldn't want to do it by hand, but probably something like Excel would probably help you out in sort of graphing that. And we can use this to solve for the 2 things that it's asking for. It's asking for what is the activation energy and basically what is the frequency factor. So frequency factor, again, is A. Activation energy is our E of A. So again, we have our equation that we had previously, which is, again, the natural log of K is equal to minus E of A over R 1 over T plus our natural log of A. So this is y is equal to mx plus b. So to find first off the activation energy, we see that it is equal basically the slope here. So the slope would equal minus E of A over R. The slope would be taken right here from the equation. So this is the slope of the line. And you would want to, again, keep the negative here. So that would give us negative 1.12 times 10 to the 4 is equal to minus E of A over R, which is our 8.314 joules per Kelvin per mole. We're basically going to multiply the 8.314 to the other side, minus 1.12 to the 4 times 8.314, going to get us something like, we'll call it 93,117 joules. 93,117 joules is equal to E of A. Again, our activation energy is usually given in kilojoules, so maybe something like 93.1 kilojoules would be our activation energy. Again, this is why the negative is important here, because that negative and that negative turns our activation energy into a positive number, which is what it should be. Any questions on sort of how we got to that there? Now, the other thing that it's looking for is the frequency factor. So we could also see that the frequency factor equals the y-intercept, not really the natural log of the frequency factor equals the y-intercept. So the natural log of A equals B. B in this graph here is 26.8. So that means the natural log of A is equal to 26.8. We would need to take the E of both sides like we did a little bit earlier. And if you do that, you get an A that is equal to, in this case, we'll call it 4.36 times 10 to the 11. And as I was mentioning before, the units here are going to be the same units that we have for a rate constant, and they will be molarity seconds, basically 1 over molar seconds. And that's because essentially this is the natural log of A, which is the y-intercept. So if you took it technically the y-intercept is the natural log of K. So when we do the E part, it actually becomes the same units as K. So that's sort of how we get back to the sort of units associated with it. Easier way just to remember is usually, again, is just the same units that you see for your rate constant. So this is, again, sort of graphically how you would solve this. And if you happen to do some problems out of textbook or something like that, there are going to be problems where the best way to sort of answer them is you can ask to kind of use something like Excel to make a graph or something like that to sort of figure it out, unless you're really good at graphing things by hands and figuring out slopes and that type of stuff, which I wouldn't recommend probably. Any questions on sort of the graphical version of this equation here? And again, that's basically what we just did there. All right, so nobody likes to make graphs all the time. So there is sort of a mathematical relationship of this equation, which is sometimes referred to as the 2-point form, which basically just means you need 2 points along that line, and you could basically just plug and chug it into this equation here. And this is, again, probably most often how you would use sort of this. And this is sort of all the same stuff. It's just basically 2 points along that graph. Basically, natural log of K2 divided by K1. So these are 2 different rate constants at different temperatures. The important part here is mathematically, people sometimes screw this up. You want to divide first and then take the natural log of it. Don't take the natural log of both of them and all that. So you want to divide, then take the natural log. Our E of A is, again, our activation energy, and our R is the same gas constant, which is our 8.314 joules per Kelvin per mole. This is more often where people run into problems in this sort of mathematical relationship in terms of those units. So again, typically our guy on top is going to be kilojoules, guy on the bottom going to be joules. So you want to watch that out. And then obviously this is Kelvin on these temperatures on the bottom here. So this is one where we could use to, if we know maybe 2 rate constants and 1 temperature, what the final temperature might be. If we know two temperatures and a rate constant, we could figure out what the rate constant would be. If we know both rate constants and two temperatures, we can figure out the activation energy. So it's a very useful sort of equation. And probably the way you most often will use this sort of equation here is sort of in this form, the mathematical relationship. So why don't you try one just to make sure here. We want to find the activation energy here in this situation. So see what you come up with. Negative or anything here. You really can label whatever ones you want, whichever ones or twos. Most of the time, people just go kind of in order. So we'll call this K1, which is 2.57. We'll call T1 701. K2 is 567, and T2 being 895. Our temperatures are already in Kelvin, so we're good to go. So we really can just kind of plug into here. So natural log of our second one, which is 567, divided by our 2.57, going to equal our E of A divided by our R, which is our 8.314 joules Kelvin mole. 1 over our first temperature, again, it's in Kelvin, so we're good on that, minus 1 over our second, which is also in Kelvin. So all that's good. So if we do a little cleaning up here on the left-hand side, 567 divided by 2.57, and then take the natural log of it, you get something like 5.39645 equals E of A over 8.314. And then if we kind of clean up what's in the parentheses there, we end up with, looks like a lot of zeros there, 0.000309. We basically need to multiply 8.314 to the other side and also then divide actually by that, right? So we're going to take 5.39645, multiply 8.314, then take our temperature to the other side. Hopefully not losing any zeros along the way there. Ends up with an E of A of 1.45097. Again, the units are going to be joules from the rate constant there, or the gas constant. And again, turning it into more of a traditional activation energy, 145 kilojoules on that. So again, we multiplied the 8.314 to the other side, and then we divided by this number to get there. Any questions on temperature Arrhenius equation? Again, probably the more way you would use this equation is more this mathematical sort of approach. Any questions on that? So overall take-home message obviously is, as we sort of talked about before, the reaction rate is obviously increased by temperature. Increase in temperature increases the rate of the reaction. Decrease in the temperature slows down the rate of the reaction. Speaking of sort of rates of reactions and what we're talking about here, which is activation energy, right? Which again is that hill. Another way that you can sort of speed up a reaction is by the use of a catalyst. Again, as we talked about a little bit earlier in this chapter, a catalyst is not a reactant. It's not a product. It doesn't get used up in the chemical reaction. It's really just there to facilitate the reaction occurring faster. So maybe that allows everybody to come to a central location to sort of react instead of just kind of floating around trying to find each other. Maybe that's, again, sort of a medium where you need maybe a low pH or something like that to sort of help everybody come together. But ultimately, how a catalyst sort of works and really how it speeds up their chemical reaction, since we're talking about activation energy, is it's able to lower the activation energy. So by finding that sort of alternative path, it's able to sort of lower that activation energy. And by lowering that activation energy by sort of following an alternative pathway, it's able to basically speed up that chemical reaction. So a catalyst is a very common way that you could speed up a chemical reaction. And again, not considered a product or a reactant, not used up in the reaction, still there at the end, but it just really finds sort of an alternative pathway for a reaction to take place. Any questions on that there? So we'll just finish up just briefly talking a little bit about mechanisms and sort of what that is. We're not going to go probably great detail into it, but this is just a picture to indicate sort of what we were talking about earlier. Not all sort of collisions will result in products being formed. They do need to hit each other in the right location with the right amount of energy. So that is the case up here. Sort of the orange and purple part hitting each other is sort of the right spot. But if the orange and the carbon down here basically hit each other, you're not going to really get any products being formed. Again, it needs to be sort of the active spot, if you will, and with the right amount of energy for a reaction basically to take place. So sometimes people think every collision results in some type of reaction taking place, and that's not really always the case. So how do reactions take place? Not all reactions are like A plus B goes to E plus F sort of situation. It's not like a one step process a lot of times, although we usually think about reactions in that sort of sense. Sometimes it may be multiple steps that occur. So maybe first happens A plus B goes to C plus D, maybe C plus D then make E plus F. And if you add those together, everything on the left hand side and right hand side that's the same will cancel, kind of like in redox. And everybody on the left stays on the left, everybody on the right stays on the right. And sometimes it is a sort of a multiple sort of step process for a reaction to take place. And reaction mechanisms try to give a possible way a reaction could take place. It doesn't necessarily mean that it will always happen that way, or that's 100% of the time the way it happens, but it's sort of a plausible explanation as to how a reaction could take place. A reaction mechanism is based on what are referred to as elementary steps or elementary reactions. And these are just a set of sequence of steps that occur that basically leads you to your overall final reaction. So if we actually talked about Hess's law in this class, like we used to years ago, you'll talk about it next semester, you would understand that, a very common way of seeing that is when you talk about Hess's law, which is basically just adding a bunch of individual reactions to try to make an overall reaction. So an example of this is this overall reaction here. When we do this overall reaction and they sort of test and monitor it, they do see the production of N2O2 sort of occurring during this reaction. But if we look at the overall reaction here, there's absolutely no N2O2 present. So what this means is this indicates that this reaction is not a one step and done type situation. It's not just everybody's going to products. There has to be perhaps multiple steps that occur in this reaction. And one plausible explanation for that is that it occurs via these two individual steps, which are referred to as elementary steps. And one explanation is maybe two NOs come together to form that N2O2, which is why it can be detected when this reaction takes place. But then very quickly, that N2O2 then gets used up and forms our product. So if we were to add these reactions together, what we would end up with is that N2O2 actually disappearing. And we do end up with the overall reaction that we were looking for in this case. And when we do get something that appears early on in the mechanism but gets used up, that guy is what is referred to as an intermediate. So an intermediate in a chemical reaction mechanism is something that's made early on in the mechanism but gets completely used up, which means you do not see it at the end of the reaction. It is not present at the end of the reaction. And so here's sort of a graphical representation of that happening. We sort of make that intermediate. It again gets used up. And in this case, again, obviously our N2O2 would be the intermediate in this reaction. When we look at these elementary steps, we can classify them as being unimolecular, which means there's basically just one molecule reacting on the reactant side. It could be bimolecular, which means there's two reactants reacting, or termolecular, which means that there are three reactants reacting. Each of these elementary steps here would be considered bimolecular, right? They both have two molecules reacting here. Now, when you're doing a mechanism, and only when you're sort of dealing with a mechanism, For the elementary steps, you could actually write rate laws using the coefficients. So this is the one and only place in sort of kinetics where you can use the coefficients in the balanced equation to write a rate law. So here the coefficient is 1. So if we were to write the rate law for this guy, it'd be the rate is equal to k times a to the 1. Here, the coefficient is 1 and 1, which means the rate for this elementary step would be k times a to the 1 and b to the 1. And obviously, this is basically 2a goes to products, which is where the 2 comes from. So if you're trying to determine, and something that you could do with mechanisms is to try to determine, is this a good mechanism? Is this a bad mechanism? In that process, you sometimes need to write a rate law for an elementary step. And that, again, is the only situation that you can actually use the coefficients. If it's something like we talked about previously, where we're not doing mechanisms, which would be the case in this class, by the way, you cannot do that. But again, it's just for mechanism, you can actually do that. How do we know if a mechanism is a good mechanism or not? Basically, there's two things that has to happen for you to say this is perhaps a good mechanism. The first thing is pretty simple. If you take up all the individual steps that are given to you, all the individual reactions, and you add them together and cancel out whatever will cancel out on the left-hand side, whatever will cancel out on the right-hand side, and you're left with the overall reaction you're looking for, then it's still a good mechanism. If you happen to add up all the individual steps and they don't add up to the overall reaction, then it's a crappy mechanism. It's no good at that point. You could pretty much stop. The second thing that's really important is there is something known as the rate determining step. It is sometimes referred to as the RDS, for surprisingly rate determining step. It is the slow step in the mechanism. So it is the step that basically determines how fast or slow a particular reaction will take place. So maybe you have 3 elementary steps in a mechanism. One of them is the rate determining step. And it's really that step that determines how fast or slow that overall reaction would take place. It's like the guy in the 10 items or less line with you that's in front of you with 500 items. You are not getting through that aisle, obviously, until he gets through. Is your rate determining step. So the rate determining step really is the one that determines it, hence the turtle there on the bottom. It is a slow step. Typically speaking, when you're looking at sort of mechanisms and you're looking at the rate determining step, those rate laws that you could write for the rate determining step should match the one that's found experimentally. And what that means is typically they'll tell you experimentally the rate law for this mechanism or reaction was found to be this. You would look at your elementary steps and find the slow step, and it should have the exact same rate law. If you wrote it kind of like what they did up here, they should match. And if they do match, then it's a good mechanism. How can you tell if it's a rate determining step or not? A lot of times in mechanisms, they write something next to each step like fast or slow. So very easily, the slow step is the rate determining step. So that's a very common way that you could figure it out. Any questions on just a very brief mechanism talk? We will lay it up there for today, the semester, the year, all that good stuff. Yes. Any questions on any stuff we talked about? I'm sure questions going